Today I'll be talking about straggler mitigation in approximation analytics. This is a system GRASS and is joint work with folks at Berkeley, USC, and Caltech. By many accounts, the next generation of analytics is focused on providing timely results, even if not completely accurate. Such approximation analytics are made necessary by the fact that we have an enormous amount of data being generated, and typically processing all of them is going to take prohibitively long. Now, there have been plenty of efforts in terms of building computational frameworks for approximation analytics, both in the open source world as well as proprietary frameworks. BlinkDB is something from the open source world. There's Presto, there's ones from Amazon, Google, and such. In all these frameworks, approximation is explored on two dimensions, or axis if you would. One is deadline, which is to say that maximize the accuracy of the result that you can provide within a certain deadline bound that I'm going to give you. An example of that is either interactive analysis or something automated that says, pick me the best ad that I can display now and I don't have forever. On the other side, you could explore it in terms of error, which is to say that I need a result of a certain accuracy or a certain error bound. Minimize the time taken to provide this result. I don't care the exact number of cars sold, but something to the nearest 1,000, nearest 10,000, for example. And our claim is that approximation analytics require a new class of scheduling design decisions. In fact, an optimal scheduler that's focused for approximation analytics knows the approximation bounds of the jobs, has an oracle about the task durations. In production workloads that I would be talking about from Facebook and Bing, we see that this scheduler can improve the accuracy of deadline-bound jobs by nearly 50% and speed up the error-bound jobs by 40%. In production clusters, talking of tens of thousands of machines, these are sizable numbers. So what about the optimal scheduler that makes it happen or important? What is the scheduling challenge here? The main challenge here is prioritization of tasks. And what I mean by that is that approximation jobs typically spawn a job on a large data set, consists of many tasks. Only a subset of them have to finish. This is the subset that would finish by the deadline for a deadline-bound job, or the subset that has to finish for an error-bound job to meet the error bound. Typically, the accuracy of the result is proportional to the number of tasks finished, and task is the finest granularity of computation that the framework sees. Also, the number of tasks is much higher than the number of slots that are available in the cluster, hence only a fraction of them run at a time. We call them multi-wave jobs, if you would. Prioritizing tasks for sort of like approximation jobs is a classical scheduling problem. And the problem is known to be NP-hard, but there are many heuristics that work pretty well. But these heuristics assume that you know the task durations a priori. And this assumption is problematic in real clusters because of stragglers. Stragglers are roughly tasks that take much longer than the other tasks in the job. In fact, in these clusters, the slowest task can be as slow as 8 times than the median task of that job. And the standard way, or the most widely used way, to deal with stragglers is speculation. As we learned from James Stark, this is a technique from the 1960s. And the idea is to spawn a duplicate for a straggler and pick the one that's the earliest in deployment in many of the clusters that we know of. Hence, given this need for prioritization and stragglers, the challenge can be condensed to saying we need to dynamically prioritize between scheduling speculative copies for stragglers and picking unscheduled tasks, keeping in mind the deadline or the error bound that we have to meet. This dynamic prioritization is important because stragglers incur an opportunity cost in that they require extra resources. Take a cluster, a simple example. For cluster, has 3 slots, a job where 2 of its tasks, are running. T2, task 2 is just finished. We are at time 5 right now. T1 isn't finished. And our estimates say that if I let T1 run, that's going to take 5 more time units, so finish at time 10. Now I have two options here. One is to go ahead and schedule a speculative copy for T1. The T1 now speeds up, it used to finish at 10, now it would finish at 9 now. Or what I can do is to say, that's fine, I'd let T1 run as it is, but use the third slot that I have to schedule another task. This is the central question here. It is that when I speculate, is speculation worth the payoff? As you can guess, the answer to this question depends on what the task durations are, as well as what the requirements for the deadline or the accuracy is. The rest of the talk, first I would present two natural scheduling designs that are based on this notion of opportunity cost, and then proceed to see how we can combine these two designs, and finally evaluate graphs. For the scheduling design decisions, of course, I'll stick to deadline-bound jobs, but the algorithms for error-bound jobs would be analogous. So a natural option if we have to schedule is to do something greedily, which is that for deadline-bound jobs, what we do is to pick the task that's going to improve the accuracy the earliest at present. Finish the shortest remaining task. Say a cluster, this has 2 slots. I can remember multi-wave jobs that I said. This is a wave width of 2. There are multiple tasks. 2 of them are running at a time. And at time 1, when T2 is just finished, we see these are how the estimates look like for the remaining tasks. Of course, this job has 9 tasks here. For T1 that's still running, clearly its remaining time is 5. It's going to take 5 more time units, but a new copy would just take 2. It's a straggler. The question is, if I have to do it greedily, this algorithm would pick the earliest finishing task. Hence, it's not going to schedule any speculative copy, but schedule T3 and so forth, because those are the ones with the smallest remaining time. All along, T1, of course, gets to run as it is. And by the time the deadline hits of 6, we've completed 7 of the 9 tasks. Of course, this does not consider the opportunity cost of speculation here. So an alternative approach, naturally, is something that does consider the opportunity cost of speculation. We call that RAS for resource-aware scheduling. This speculates if it saves both time as well as resources. What I mean by that is the following. Take the same example of before. Now we have 2 slots, T1 and T2 are running. T1 is a straggler, T2 just finished. These are the same time estimates as we have from before. So at this point, when I have to think about whether I should speculate for T1, I basically would have to consider if I could just let T1 run, which is 1 copy for 5 seconds, or maybe schedule another one, which would be 2 copies, but only for 2 seconds. In terms of the calculation here, you could see that speculation would save resources. So what I end up doing is schedule a speculative copy for T1. That's the one in lighter blue, shade of blue. And then at that point, of course, the unfinished copy of T1 is killed. And then we schedule the other tasks. And we end up finishing 8 out of the 9 tasks in that job. Hence, if we compare these two options, GS, which is a greedy version, RAS, which is a resource-aware version, we see the following, that in the specific examples that we ran through, GS has a lower accuracy than RAS. However, if I were to change the game here and push the deadline to 3, then GS has finished 3 of the 9 tasks, RAS has finished only 2. In other words, what we're seeing here is that neither GS nor RAS is uniformly better than the other. When the deadline's large, looks like RAS is better. If not, we should do the more greedy option. Or in other words, when there is more time remaining, be more smart about the resources that you're going to use. But when it is close to hitting the deadline, be more aggressive. So this is the intuition that we have in terms of how we could combine these two. Start off with RAS early in the job, which is to be conservative. and towards the end, at some point, switch to GS. Now, how good is this intuition? And when exactly to switch? To that, we resort to a theoretical scheduling model. This is a scheduling model from first principles. It considers multi-waved scheduling of tasks, where the wave width is assumed to be constant. Now, the wave width is a function of the fairness policies in the cluster. It says this is how many slots you get to use at any time. Now, we are agnostic to that. We just require what the wave width is. And task distributions are heavy-tailed. And this is something we verified in our traces that they do follow Pareto distribution. Among many speculation policies, both proactive and reactive, we of course consider GS, RAS, the switching one with various options of when to switch, and an optimal. Under this model, a result that we have is that using RAS, when more than 2 waves of tasks remain, and switching to GS for the last 2 is near optimal. For more details about it, of course, I would refer you to the paper. So this was good in that now we have a validation for our switching, intuition, and we also seem to know when we have to switch now. But in practice, how do we estimate 2 remaining waves? Now, obviously, the theory simplified things a little bit in that it assumed that wave boundaries were strict. There was like, but that's not really true because, in practice, as and when old tasks finish, new tasks get scheduled. Further, even the wave width is not constant throughout the time of a job. Recall that I said wave width was a function of the fairness scheduler. Now, of course, as and when new tasks come in or old tasks leave, your wave width is going to change because you'll get more or less slots to use at a time. Hence, we relax the scheduling, the result from the previous slide to say that I would start with RAS. Switching is good. I'll keep switching, but not necessarily at 2 waves, but somewhere close to the deadline or the error bound. Now, how close this should be? We use a learning technique from empirical values here. Now, assume that we had enough samples of a job running for various deadlines purely with just RAS or just GS. Say a job has a deadline of 6 as before and is run for 4 units of time. It is started with RAS, and so it's still with the more conservative, the resource-aware option. So at this point, the options that I could do is to switch to GAS right now. The one on the right would calculate the accuracy of what would happen from other previous job samples that I've had. RAS of 4 seconds, GS of 2. Or I could wait and say that, if I didn't switch now, but switched 1 second from now, what's the accuracy that I would expect? Or never switch. Among these 3 options, remember that we are at time 4 right now. Among these 3 options, I would switch if the best option is the one on top. Because the one on top was to say that if I switch right now, what would happen? If that gives the best accuracy, then I switch. If not, I wait for later. And then periodically, in our experiments, we do it every second, we see what the accuracies are going to be and whether the switching point has to be now. Recall that this, of course, assumes that we have sufficient number of samples, job samples. When I say job samples, I mean accuracy with running just GS or just the RAS algorithms. This, of course, represents a trade-off that is more widely known as the exploration-exploitation trade-off. The more samples I can get, the better my calculations are going to be. However, for me to generate more samples, those jobs that have been enlisted to generate those samples, of course, lose out on performance because they don't switch. They stick to one of them statically. For some people familiar in the audience, this is a kind of a multi-armed bandit problem. And we use solutions that are fairly standard in that space. We use an epsilon, more specifically of 10% or 0.1, which is the probability with which you decide whether you want to generate a sample. Therefore, to put it together, our scheduler that we call GRASS relies on the fact that speculation has an opportunity cost. So based on this notion of opportunity cost, the two kinds of scheduling algorithms that we looked at, one that's more greedy, which is it doesn't care about the opportunity cost, but just wants to improve the result the best at that point, or something that's more aware of the opportunity cost. We have an algorithm graph that starts with the one that is conservative about the opportunity cost and switches to the more aggressive option closer to the deadline or error bound. We learn the switching point empirically from job samples. And the switching algorithm that we have can be proved to be near optimal in our theoretical model. We've implemented graphs inside of two big data frameworks that are there, Hadoop and Spark. We've modified the FAIR scheduler in these frameworks, and we use both these frameworks mainly to get a sense for both the general applicability of our algorithm, as well as to expose our evaluation to various kinds of stragglers. Hadoop is more disk bound. Spark does most of its stuff from memory. So just throwing the thing at various kinds of systemic factors that can bring in stragglers. The two things that the two things that are required for task estimation that we used earlier, which was the amount of remaining time and the new time. For that, we modified the estimators itself, where tasks would periodically report progress reports. We used a simple technique where the remaining time is extrapolated from the amount of data that's remaining to be processed. More sophisticated techniques could be thrown in, but this worked sufficiently well for our purposes. And the time taken for a new copy is sampled from the completed tasks. So how well does GRAS actually perform? We use the same workloads that I talked about from earlier. These are large production clusters, running both Hadoop and Dryad jobs. And to these jobs, these were obviously not approximation jobs, but these were jobs to which we added, approximation requirements. We added deadline requirements by computing what an ideal duration of the job has to be, and then gave a certain amount of elements on top of that ideal duration. And error bounds we picked randomly chosen between 0 and 30%. Our baselines are the speculation algorithms that are running in these clusters right now, late and monthly. And our deployment was on EC2 on a 200 node cluster with 2x large instances. First, we look at deadline bound jobs, and we see that their accuracy on an average improves by 47%. And these gains hold across all values of deadlines, if you would, both the lenient ones as well as the stringent ones. In fact, this graph here on the x-axis plots that elements that we added on top of the ideal duration. And we see that across all these values, gains vary from 35 all the way to more than 45%. In fact, GRAS is much better than statically picking just GS or RAS as well. This graph plots the gains that we see, where the gains are diced according to the size of the job, or job bins, if you would. Job bin. And we see that in each of these job bins, we see that GRAS is better than the best of the two options, the GS or RAS. And not only this, GRAS's performance actually matches an optimal. Finally, if you look at error-bound jobs, they achieve a speed up of nearly 38% as well. And as before, the gains hold across all the error bounds. In fact, a nice a result that also comes out is that exact jobs, which are jobs, if you would, with 0% error bound, which is they have to finish all their tasks, even they speed up by over 30%. So this makes GRAS a unified straggler mitigation solution for clusters that run exact jobs today or approximation jobs going in the future. So to conclude, we said the next generation of analytics would be focused on providing approximate but timely results. And for scheduling for approximation jobs, the main challenge is in handling the stragglers that are often dynamic and unpredictable. we came up with a solution graphs that weighs the opportunity cost for speculating for stragglers, be conservative early on, be aggressive towards the end. And our evaluation was in Hadoop and Spark, and we got near optimal results in terms of speeding up error-bound jobs as well as improving the accuracy for deadline-bound jobs. Thanks. Be happy to take questions now.
Hey, nice work.
Thanks.
Have you looked into the possibility of killing off stragglers rather than waiting for them to finish?
The possibility of killing off the stragglers?
Yes.
Yes, these things assume that at some point when you when you have two copies running and one of them is too slow, then at that point the slower copy is killed off.
Mm-hmm.
So if the approximation bounds can be met by just ignoring the stragglers, if you would, that's already part of the thing. But yeah, there are many stragglers many jobs for which that's not sufficient, and mainly because of the fact that often stragglers also occur a task is not uniformly a straggler, but they start straggling at much later points and such. So it's hard to see when a task starts straggling and things like that.
Right. Thanks.
Hey, Roger.
Really elegant work, Rodrigo from Brown. So one question is, did you find jobs in which the duration of a task might be dependent on the data of that particular task is handling? And in that case, the greedy solution, if you're doing approximation, it might bias the result of your approximation. Did you find any effect of that?
That's a good question. Your question is more like not all tasks are equal. Is that kind of what you're getting to?
Like if a task of a that deals with particular data happens to always take longer, you might end up never running that task in lieu of other tasks, and then your approximation results might be biased, like you're approximating but in a biased way.
Right. Yeah. That's a good point, and that's something that we do not take care into the system at this point. At this point we assume all tasks are the same and weigh equally. But if such an information was there that we could provide out of band to the scheduler, then that is something it can take care in terms of calculating the accuracy values that it would get.
Right.
Yeah. Thanks. Cool. Thanks.